Hello everyone, welcome to Global Institute of Innovation and Entrepreneurship's presentation on 3D geometry. Today we will investigate how to find the equation of a plane. So before we jump into 3D geometry, let's just recollect some facts about the equation of a straight line in 2 dimensions. So I have the 2-dimensional plane. I have my x-axis, I have my y-axis, and I want to figure out what is the equation of the straight line in 2 dimensions. Typically, how can I do this? Okay, if I'm given 2 points on this line, say x1, y1, and x2, y2, once I'm given these 2 points, I can write the equation of the straight line that passes through these 2 points. So in this case, we'll have y minus y1 by x minus x1 equals y2 minus y1 by x2 minus x1. So I want to now extend this idea from 2 dimensions where I had a straight line on the xy plane to 3 dimensions where I have something like a plane. So imagine this to be a plane in 3 dimensions. This keeps extending both to the right and to the left and upwards and downwards. I want to find what is the equation of this plane in 3-dimensional space. So how would I go about doing it? So let's first characterize what are the times when I can find the equation of a plane. So first let's set that up. A plane is uniquely determined if 1. The normal to the plane and its distance from the origin is given. So take for example I have these 3 dimensions x, y and z, and I want to find the equation of the plane which has this part as part of it. So probably the equation of the plane is like this. The plane goes like that. I want to find what is the equation of this plane. Now, what do I need for that? I want the equation of this plane here. So now, I need to know what is the normal to this plane. So if you can look at the marker, it is normal to this plane. So I need to know the normal. What is the normal? And suppose I have the 3-dimensional coordinates. What is the distance of this plane from the origin. So along the normal from the origin, how far is this plane? That is what I want to know. Once I am given the normal, once I know the normal to the plane and its distance from the origin, I'll be able to find the equation of the plane. Next, the second case is when the plane passes through a point and it is perpendicular to a given direction. Right? This is like the point slope form of a straight line. Once I know a point through which the straight line passes and I know the slope, I can exactly tell what is the equation of a straight line. Similarly, if I know that the plane passes through a point and I know that it is perpendicular to a given direction, I can immediately find what is the equation of a plane. And the third case is when it passes through three given non-collinear points. What are collinear points and what are non-collinear points? So if I have 3 points, all of which lie on a straight line, then these points are collinear. But if I have 3 points which cannot be captured within the same straight line, then they are non-collinear. So in all these 3 cases, I will be able to find the equation of a plane. So as far as this class goes, we will concentrate on the first case. We'll worry about the other 2 cases next time. So we are going to look at how to find the equation of a plane given the normal to the plane and its distance from the origin. So let's start. Equation of a plane in normal form. Equation of a plane in normal form. So here I have, as always, the x, y, and the z axis, and here is the slice of my plane, Here is my origin. Now I'm told that there is a normal to the plane, and I'm also given the distance from the origin. So these two are given. Okay, let ON be the normal. Let ON be the normal to the plane from the origin. So here is ON. I'll call N cap be the unit normal along ON. So ON is a vector. I have this plane somewhere like this, and from the origin the normal is coming through this plane, and I want to find N cap, which is the normal vector of length 1. So I will call that the unit normal. Since this plane is at a distance, let us say from the origin, the distance of this plane is d, then what can I do? Here is ON, it comes and touches this plane here. ON is nothing but the distance of this thing here is d times the unit normal N cap. So ON vector is of length d along the direction N cap. This is given. Alright. Now let me take any point P on the plane. So here is the plane, here is the normal coming out of it. Let P be any point here. I'll mark it like this. Here is the point P. Here is the point P, and there is the normal. Fine? ON, it comes like this. If I join, as this comes out, if I join the line from P to N, what can I say for sure? Pn will be perpendicular to ON. And so, what does it mean? The inner product between Pn and ON will be equal to 0. So here I have, let's just recap it. Here I have the normal coming out. I have the normal coming out like this. Here is my point P. So I know that if I draw this line, here is N, here is P. From the origin this is coming, so ON vector will be certainly perpendicular to PN vector. And how do we capture the notion of perpendicularity? The inner product between Pn and On should be equal to 0. So this is my first equation. Now I have developed the first equation, which is Pn dot product with On, these two vectors. If I take the dot product, I should get 0. Let me call it equation number 1. Now, let R be the position vector of the point P. So if P is x, y, z, what will be R? R will be xi plus yj plus zk. Now, here is a little notational thing that we need to keep in mind. Whenever we put a vector like this, it means it is a general vector. I don't know if the magnitude of this vector is 1, but whenever I use I, it is the unit vector of length 1 in the x direction along the x-axis. So if it's a unit vector, I will use cap. So it is x I cap, y j cap, and z k cap. So whenever I see a cap, I know that the vector is of unit length. Whenever I see an arrow, I don't know what its length is. It may be 1, it may be more than 1. Fine? So now what are we given? R is the position vector of P. And ON equals D n cap. ON is the normal, it is along the unit normal n cap, it is of length D. Now I want to find what is Pn. What is Pn? It is always, with respect to origin, I will do ON vector minus OP. Right? That is Pn. And what is ON? D n cap. And what is OP? It's exactly this position vector. Right? I'll call this R. And what do I know? Pn vector is perpendicular to the vector ON. So that means Dn cap minus R dot product with ON, which is again Dn cap, this should be equal to 0. So let me write this again. Dn cap minus R dot product with D n cap is equal to 0. And what does that tell me? Immediately D is non-zero, so I don't have to care for D, I can pull it out. So D n cap minus R dot product with n is equal to 0, because D is a non-zero vector. So I'll write, since D is not equal to 0, I can divide by D. So D is gone. I'm going to take dot product. So D n cap dot product with n cap minus R dot product with n cap should be equal to 0. All I have done is distribute n cap to the first term here and the second term. So I get D n cap dot n cap minus R dot n cap should be equal to 0. But n cap is a unit vector. If I take dot product of a unit vector with itself, what will I get? I'll get 1, because the length of the unit vector is just 1. So if I take the dot product with itself, I'll get 1. So D minus R dot n cap equals 0. In other words, R dot n cap equals D. And this is the vector form of the equation of a plane in normal form. We'll stop at this. We'll explore more next time. Thank you.